We can explore the relationship between voltage, current, and resistance through Ohm's law. V is our voltage, measured in volts, the electromotive force, or the potential difference between 2 points on that circuit, is equal to I times R. I is our current, measured in amperes or amps. This is the flow of electrons. Times our resistance, measured in ohms or the omega symbol. This reduces the flow of electrons. At individual points within a circuit and the circuit as a whole, you can examine and calculate using this relationship, Ohm's law.
This is an example of a basic circuit. If you're able to open and close the circuit, you've made a switch. When I close this gap with another LED, I've created a new kind of circuit, a series circuit. Series circuits are named because each load is placed in a row. The electrons have to flow through one single path, through all loads. The resistance of each load adds up as they cause the voltage to drop more and more each time. Because of this single path, the current flows at the same rate throughout. If you add more loads, notice that the brightness of the LEDs drops. The current acts like a highway. If you add more tollways, the traffic slows down. Removing any of these LEDs stops the flow of electrons and the whole circuit dies.
A series circuit is like building a tollway on a single lane highway. All cars have to travel through all of the toll booths in a row, slowing the cars down. The cars have no optional path, just like the electrons have no optional paths. This creates one steady current with different voltage drops across each resistor. If we wanted to explain the series circuit mathematically, we could say that the total resistance in the circuit is equal to the sum of all the resistance in the circuit, since each electron has to travel through every single resistor. The total current is equal to the current at any given point. It's the same flow of electrons throughout the whole circuit. There are no other paths. And then the voltage of the power supply is the addition or the sum of the voltage drop across every single resistance. Every resistor or every bulb, every motor is going to cause a voltage drop as the electrons pass through. We can apply Ohm's law in our series circuit tendencies with this schematic diagram. Here I have a battery and 3 resistors. So I'm going to find the total resistance to begin with. Total resistance equals the sum of all resistors. So 6 plus 4 plus 14 gives me a total resistance of 24 ohms across that battery. I can now find the total current. Whenever I see 2 out of the 3 variables in my Ohm's law equation, I can always find the third. Substitute in what you know. It's a little one-step equation. Divide by 24. And the current is 0.5 amps. At this point, I can double check. Can I apply any of my tendencies? I've found the total resistance by adding all the resistors. Well, I know the total current is equal to the current at every other point throughout. And I know the total voltage will be the sum of all the voltage drops. So I can apply right now the total current at each point. Then I see now I have R and I at each point. I can apply Ohm's law again. I'm going to substitute in what I know, solve for what I don't, and keep repeating it until every V, I, and R is solved in the circuit. I can even double check my work. 7 plus 3 plus 2 equals 12 volts.
Electrons travel through a path of least resistance. So if I add a line of Play-Doh here, the electrons will go through it instead of the LED. If I add an LED to this new Play-Doh, I've created a parallel circuit. Parallel circuits are named as such since electrons follow multiple or parallel paths, not just one. Since electrons can travel through multiple paths, the voltage is always the same or constant across each load. As I add resistance to the circuit, the LEDs do not drop because the resistance is inverse. Because of this, the current is different along each rung of the parallel circuit, which looks like a ladder. If I remove LEDs, the electrons just simply take another path. So you can remove an LED from a parallel circuit without the other bulbs turning off.
A parallel circuit acts like a multi-lane toll booth. The cars now have optional paths, so they travel through each booth at different speeds. optional paths for electrons create differing currents. Even though the cars travel at different speeds through the booth, they're all pushed along by the same amount of cars behind them on the road. As the electrons flow at different currents, they still have that same voltage pushing them along through each of the paths. To help apply Ohm's law, we can explain these tendencies mathematically. Because of that inverse relationship with resistance, the inverse resistance of the total circuit is equal to the inverse resistance of all other resistors in that circuit. The current is the sum. Because we have multiple currents, you have to add them up to get the total current. It's not the same throughout. And then the total voltage is the same at every single point. This is why parallel circuits allow bulbs or loads to continue to work even if another resistor or bulb was removed. We can apply Ohm's law and the tendencies to this parallel circuit. I see 3 resistors in a row. They kind of look like a ladder. That's parallel. I'm going to take those resistances and add their inverses, or 1 over. Now that gives me the inverse of my total resistance. So it's not 0.5, but 1 over 0.5 gives me 2 ohms. Whenever I see 2 out of my 3 variables in Ohm's law, I can always solve for the third. I know voltage, I know resistance, so I can calculate the current. Substitute in what you know, solve for what you don't. Now at this point, I need to try to apply my tendencies. We already found resistance using our inverse button on our calculator. The total current is the sum, so those other 3 resistors all have to have currents that add up to 6. And then I know that the voltage at the power supply for the whole circuit is equal to the voltage drop at each of those resistances. So that means that 12 volts, 12 volts, and 12 volts at each point, because we have that equal force, that equal push of electrons through each one. Now we can apply Ohm's law. If I have 2 variables, I can solve for the third. Substitute in, solve for what you don't know. Substitute in, solve for what you don't know. And yet again, substitute and solve. You can even double check your work. 1 plus 3 plus 2 is 6 amps. I expected a total current of 6 amps.